Thank you for giving me the opportunity to speak here today. So just a little bit of insight in Imperial College. Well, I'm pretty sure that Imperial College of London is quite well known to many of you, if not to all of you. Well, I'm going to talk about one of the research groups from Imperial College. But however, I just want to mention one important thing. And that is the fact that Imperial College has about 7 research teams, which are ranging from computer systems to AI and to biomedical engineering for computing systems. However, out of those 7 teams, only one of them is mainly focusing on machine learning. The rest are not, but they deal with machine learning on a day-to-day basis, applying it to their application. Our group, which I'm part of, is the custom computing group, and this group is actually focusing on providing research for different very efficient, performant, and productive tools using hardware acceleration. Now, just as a simple introduction in our group, well, let's think of the following scenario. In an ideal world, you will be able to build a computer chip which is literally customized for the task that you want to run your program on, and then you want to program it in order to be able to fine-tune its performance. Well, however, fabricating such a chip is very, very expensive. And FPGA technology like Xilinx and Altera are taking the fabricating process out of it, and they are introducing these customizable chips which are reconfigurable designs, and they use hardware level programming. Now, FPGAs, which is, you can see one picture of an FPGA chip in the center there. FPGAs are just containing gates and building blocks whose connections are reprogrammable by passing electrical signals into them. So this reprogrammable chip can then be used like an Intel chip. And actually, talking about Intel recently announced their collaboration with FPGAs, and that's happening because they recently bought Altera. And they are having some new chips which are using Intel Atom and Intel Xeon. And on the same chip, they have an FPGA board from Altera Aria. So hopefully this will make it more and more easy for us to program on them. So in terms of the next generation computing, the existing computers are slow, they're power hungry, and sometimes it's actually complex to implement applications on them. So our main focus is really to customize these hardware and software solutions. And we are doing so by enhancing the design quality and the designer productivity. So the research strategy is really focusing on those FPGAs, which are giving us reconfigurable acceleration. And you will see me using a lot the word DFE throughout my slides. DFE, I'll introduce you now, is what we call a data flow engine. And this data flow engine is made out of an FPGA, the memory, and the data flow. So some of the hardware devices that we have are actually quite impressive, I think, for a university. So, for example, we have 3 MPCX nodes with 8 cards each with Stratix 5 FPGAs on them. The actual measured main memory throughput on those is 65 gig per second. So essentially, we could potentially access about 130 petabytes per day of potential processing. Then we have just another 10 FPGAs, which are static and independent boards. We have 6 GPUs. Out of them, some are very new ones, like NVIDIA Kepler, K40, K80. And then we also have a high-performance center, which I won't mention here, but it's quite impressive one, because if you look at the CX1, it has about 1,400 nodes and about 14,000 cores. So it's quite impressive for a university. Now I want, before I go in the applications that our group does and how we employ machine learning, I want to start with a little quote from actually a blog that I was reading about, I think about a year ago. And this blog is written by MapR, and it's about the Large Synoptic Survey Telescope. So I'll just give you a little quote, and then I'll explain to you how this relates to our research. So I'm starting the code now. The Large Synoptic Survey Telescope will generate 30 terabytes of image data per night, every night, for 10 years. By the end of the 10 years sky survey, a final image archive of about 100 to 200 petabytes will be achieved, along with a 20 to 40 petabyte squareable database of astronomical source information. So this astronomical source information contains features extracted from the many millions of images obtained during that decade. Now, they say here that volume is a big deal, but the data velocity may be the biggest challenge. In particular, there will be one 3 gigapixel, which is approximately 6 gigabytes, image obtained with this LSST superb camera every 20 seconds every night for those 10 years. So approximately within 60 seconds, the image will actually need to be processed, and all objects in the image, the pair that have changed in any way, must be reported to the worldwide astronomical community. So it is anticipated that each image pair will generate several thousand alerts every 40 seconds again, which correspond to about 1 to 10 million alerts being sent out via individual email and text messages every single night for 10 years, of course. Joking about the email, but they're sending out every 10 years. So that's very fast, high velocity information. Thus, the ability to mine, characterize, classify, and respond to this rapid challenge and avalanche of alert will be an enormous challenge to the researching community seeking to make astronomical discoveries from this data in real time. This is where our groups come in, where we try to actually accelerate a range of real-world applications and cutting-edge technologies from deep learning, convolutional neural networks, incremental support vector machines, deep Boltzmann machines, to even normal sequential Monte Carlo methods. And we are trying to do this as close to real time as possible. So, for example, some of the applications that our group does, and some of them are finished, some of them are still ongoing, are dealing with even financial simulation. Wherever you see faster and less energy, faster is comparing to the equivalent single or multi-core implementation. And less energy is really the fact that FPGAs are much better than GPUs and CPUs in terms of the power that they provide, so they are more energy efficient. Now, some other application that we do is genomic analysis through string matching. So actually what this genomic analysis does is we're trying to accelerate DNA sequence alignment. So coming back to the previous talk, we're trying to accelerate the Bissell fit sequence alignment, which is a stage that is recently developed in bioinformatics pipelines for cancer and non-invasive parental diagnosis. And we obtained about 88 times faster than the CPU approach. Now we're doing climate modeling as well through stencil computation. We're also doing air traffic management through sequential Monte Carlo method. And we also have a number of quite powerful iterative sparse linear solvers. And those are very important, the number of applications that you find everywhere in the world. So those applications come from computational fluid dynamics to the power systems simulation. And this architecture is about 87 times faster as well. Now, some of you might think, why do we want to use the FPGAs and not GPUs? And when should we use them to try to accelerate? Well, the whole idea is, if you want latency and you care about latency, then you want to use an FPGA. And an FPGA, for example, if you have let's take a high-frequency trading system, where 1 millisecond of delay of latency will be crucial for this trading system. This is when you want to use an FPGA, because FPGAs are able to give you not only nanoseconds, but micron in terms of latency, and this is actually providing you consistent latency. So there are many other things that I could talk about in terms of advantages and disadvantages. For example, even with the energy efficiency, even with the new NVIDIA card that is available right there, the NVIDIA is maybe now reaching about 10 watts in order to be processed. However, for our FPGAs, they are much less than that. So we're still using lower power. Then, for example, when is really good to use an FPGA? Well, you can use the FPGA when you want to execute multiple tasks on the same data. However, if you want to execute the same task on multiple data entries, then you might be better off using a GPU. So now starting with how we use machine learning. Well, of course, we use machine learning to accelerate some machine learning applications. However, we also use machine learning in our day-to-day programming on FPGAs, in what we do. So there is this interesting research that one of our colleagues who recently graduated was working on, which is called the multi-objective machine learning optimizer. And he's making use of Gaussian process regression, support vector machine classification, and particle swarm optimizations in order to try to self-optimize our reconfigurable designs through automatic analysis and adaptation on the design parameters. So what does that mean? Well, we have some design parameters when we construct our reconfigurable designs. And actually, those are really important because for us, in order to compile even a simple application, which someone might think it is simple, let's say a genetic algorithm built on the FPGA would take about 8 hours to be compiled. Well, the fact is, in these 8 hours, the application can run up to 6 hours. And after 6 hours, if it is an error, it will throw an error and you'll lose it. So we care about trying to optimize as much as we can those design parameters. So we use even cutting-edge technologies like machine learning in order to do that and be fast and try to avoid those situations in our designs. So now the other, of course, approach that we're taking with our research group is really just machine learning applications. So for example, the neural networks simulation for a polychronous spiking neural network. Then we actually have one of our guys who implemented a pipeline genetic propagation algorithm. So it's just a genetic algorithm. However, he built his own version of it on FPGA, and he obtains like, 90 times faster in terms of performance for speed up compared to a highly optimized tool for CPU, C++ implementation for the traveling salesman problem. However, he uses this even in normal stock trading and other applications as well, and it gives very good results. The other applications that we are working on at the moment, one of them is incremental support vector machine. So that's actually used, and the way we are testing it is for stock trading. And we obtain about 41 times faster acceleration, and again, this acceleration is compared to a highly optimized 12-core CPU implementation. And then we use these machine learning techniques for some other real-world applications like network anomaly detection. So the network anomaly detection, for example, the one closed support vector machine was trying to do is trying to identify a class int, a training data that you have, a certain class of elements. So you're getting in a network anomaly detection, what you will do, you will try to detect any abnormalities that can appear in that network. So you're trying to really predict the attacks, the cybernetic attacks, faster than what is happening nowadays. And this was successful. And then really we're focusing all the time on trying to accelerate financial applications on DFEs. So the challenges here on financial applications, as we all know, is the fact that we have a large amount of data to process. So you take high-frequency trading, you will have a lot of data. The speed of processing, as I said before, is crucial. So the latency in which you process this data is very important. And of course, we need to consider the accuracy of results. So all of this, in order to build our designs, we need to take care of the precision that we're building our designs in, and then we need to account for the best trade-off between speed up and accuracy, and of course, resource utilization. So for example, one of the recent works that I've been working on is a genetic programming system for trading. So just as a quick overview, you have some, I'll just give an insight of the genetic program as well on how it works. So you have a population of trading rules. Trading rules in our work, they are represented by binary expression trees. And those binary expression trees, really behind them, they're just mathematical formulas. So we generate those binary expression trees on the CPU. For the scope of this, we will generate about like 1,000 of them, of individuals. And afterwards, we try to determine each individual's fitness. We do this by using the fitness evaluation cumulative return. which is from finance. And then we are selecting the best performers individual, which is the best half. We're going in the next generation. In the next generation, we apply the genetic operators like mutation, crossover, and reproduction on it. And afterwards, we are applying this into the next generation, those individuals newly produced, with the best performing ones as well. We introduce them again, and we perform this until the algorithm converges. However, in our case, because we want to maximize profit, we will make it for a number of n generations. Let's take 10,000 by example. So from the recent studies, really the individual fitness evaluation is the part that takes up to 95% of the execution time. So this is the time that we focused on accelerating on the FPGA. And now we obtain some good results. So in this graph, we are showing results from some historical data from 2003. Is GBP, USD currency data in high frequency trading. However, the number of ticks per second there was quite low. It's not like now, but unfortunately we didn't have newer data. We did, however, test this on synthetically generated data as well. So what we can see is that, for example, when you have about 992 expressions and 19.2 million data points, which is approximately 2 gigabytes, then we are reaching a 20 times speed up. Now the speed up increases with the number of expressions and the number of market ticks. Of course, as we probably everyone would expect. So what I wanted to mention here is the fact that, for example, when we synthetically generated data, we tested this on 864 million data points as well, and we scaled it up to 864 billion data points as well. So just to give you an example of this kind of speed up we get, for example, when you're scaling it up to 860 billion data points, well, that will take you to about 100 terabytes of data in terms of what we are actually considering processing. And that takes approximately 31 hours on the CPU, while on the FPGA it takes about an hour. Now, what do we obtain from this? Well, we obtain about this 20 times speed up means not only the fact that we can analyze 20 times more rules, and this is important for regulators, for example, who are looking for abnormalities in the market, and they're checking to see if some trader did something wrong. But it's important from a financial institution point of view because you can analyze more trading data and you have increased latency. And we simulated one of these environments using this genetic program, and we obtained 3.5 times higher returns just because we were able to trade easier and faster. So now, in terms of some of our future works, I'm currently working on a deep Boltzmann machine for financial market direction prediction, which I'm now in an attempt to try to accelerate into the FPGA. Then we have some support vector machines for satellite image classification. And finally, we have some data analysis and clustering methods, such as DBScan, for example, that we're working on. And if you have any questions, yep.
Hello. That was a very densely packed talk, a lot of information to digest. So you mentioned that FPGAs, they were ahead of GPUs in terms of latency. So my question is if they're quicker because of their sheer, just because of the computational power, or it's mostly attributed to different input-output architecture, how the data flows to where it is processed and out of it. So this difference in latency, where does it come from? From the pure performance or because of a better architecture?
So the architecture itself is targeted for latency. And as I said before, this is really you're going to use FPGAs when you want to process multiple tasks on the same amount of data. However, you have to use GPUs because FPGAs will be slower when you want to process the same task on multiple data points because it's just the architecture is differently situated. So we're dealing with this kind of applications. But again, FPGAs are faster in some ways than GPUs, but they're faster in those applications, not in other ones.
Hi. Yeah. What's the technology stack you are using?
So we're actually using Maxeller FPGAs, which are some Xilinx and Altera boards. And Maxeller has a Maxeller IDE. The way we actually program, we don't program in VHDL or Verilog. We program in this high-level programming language, which is a mixture of Java and C. However, in order to program in that, you have to have a good understanding of the design and how it's going to work, because everything, it's like you need to think about the design of your algorithm from a streaming point of view. So you can't just think about the way you would use it normally. So you can't have random memory access really on an FPGA. You have to think from a streaming point of view. But we use these tools in our group. On the data mining, we normally, when we perform the test, because I'm one of the persons who does those tests, I'm just using R and Python and MATLAB just for some classic tests. But we focus mainly on the acceleration, and then we perform these statistics we perform to see how it is compared. Yeah.
Thanks for the talk. It was amazing. I have two questions.
Yeah.
First of all, do you plan to open source any of these implementations?
We actually do have open source. So if you will search for custom computing group research on GitHub, you'll find some of those implementations. The genetic programming one is not yet available because it's work under review. We implemented it and we improved it, and now it's under review in a journal. So we're not really allowed to show it until the journal accepts it, and then that will be on as well. But many of those that you see, they're already there. Incremental, SVM, everything is already there.
Okay, that's great. And the second question is, FPGAs are notoriously hard to program against. I mean, Verilog is complicated. Even OpenCL is considered to be high level by the FPGA guys, but it's low level from our standpoint. What's the state of the art around here? I've seen a few projects around EMD implemented something in Java and Scala to sort of make it easier to program as sort of a wrapper around OpenCL. What's the state of the art here? Are there any sort of better ways of programming FPGAs?
So I think the way, exactly what we are using, Maxeller is an easier way of programming FPGAs, because it's giving you this high-level programming language, which is really you're writing Java and a mixture of C. But again, you're writing it without being able to have objective-oriented programming. But just write a normal Java, and that's much easier from a software engineer point of view. However, you still have to get yourself in the mentality of thinking from a streaming point. Now, I know I've actually come from another talk from STAC, and Steve Weston, who's heading the Altera, the department from Intel, essentially, the hardware acceleration, he said that they are now working on some quite cool technology, which is using OpenCL, unfortunately, so exactly what you're saying, but I think OpenCL still it's a bit easier to understand than Verilog or VHDL, and they are trying to make open source libraries and frameworks available to people who try to just buy FPGAs and use them in their startups or whatever. So those libraries will be available. They're actually working on some convolution neural network library as well. So quite cool technology, and anyone should be, because they're open sourcing it, anyone should be able to contribute. But it's OpenCL.
I can ask another question if there's nobody else.
Okay.
And then I'll leave everybody else around. There is, somebody mentioned the difference in architecture between Intel CPUs on von Neumann and what FPGAs has. And one big difference is the sort of difference between local memory and global memory. How do you find that difference in architecture? Is it easy to cope with from somebody that has not worked with something like this, with a different sort of memory tiers? I mean, is it complicated to adapt, or is something that comes naturally after a while?
So it's not complicated to adapt. I'll give you a few examples. For example, in this genetic programming trading thing, we have to process a lot of data, right? And we can't really keep it on board because it will make it slow, and we don't want to do that. So what you do is really you transfer it from the CPU to the DRAM. It stays on DRAM. And then we have a so-called buffer RAM on the actual FPGA chip. And that buffer RAM is where you actually store the temporary data, so like the expressions that you need to evaluate all the time on the market data that you have, and you store them there and you perform the evaluation, and we use, like, for example, techniques like double buffering and stuff. So the moment you evaluate something, you fetch new data in. So it's actually not that hard. You still think from a point of computer science perspective to it. You just need to get used to this, like how to handle this memory. And I think the other important thing to mention here is, for example, we do use like runtime reconfiguration, so switch between designs in real time. Well, what's happening is most of those FPGAs they have like soft memory controllers. So essentially, you risk to lose the data that you have on DRAM stored. So if you can implement your algorithm in such a way that you actually keep batches of data in memory and you don't lose it and you keep it in VRAM. However, what you can do, you can actually just, if it's not that important, you can just lose it, reload it. That will take a few seconds, depending on your latency. It might be important or not, so depending what you deal with.
I think the newest ARIA chips survive reconfiguration.
Yes, the newest ARIA, they do survive.
Okay,
And
thank you.
That's
Sorry.
what Intel is trying to achieve with their CPU FPGA hybrid chips. The fact that you will have this slow transfer via the PCIe Express, which is a slow interconnect, really, you won't have it anymore because it's already on the same board, but now it's quite slow.
So a quick question. I don't pretend to understand everything you talked about, unfortunately. However, it's interesting and wondering, would you expect this technology to reach mass market? And if yes, when?
To reach what? Sorry.
Mass market, so everybody using it at some point.
Using it. I mean, for example, Maxeller built the RISC platform that JP Morgan is using at the moment. And that's public information. JP Morgan is using FPGAs for their risk management platform. And I mean, FPGAs are now more and more starting to be used in hedge funds as well for high frequency trading, where everything it's important. So you don't have a cutting edge advantage anymore by being like faster in like a little bit like 1 nanosecond. You don't. You try to improve from the fact that you buy a microwave network, for example, to improve the latency, but you also improve from having those technologies that give you just a little bit more, and that's enough for, I don't know, a few months, 1 year to take the advantage against your competitor.
How costly these machines are?
Well, depends on what you want to do with them. But I mean, I don't know, Maxeller was selling some of the ones that we're using for about 30,000. But there are some even more expensive than that. So if you look on there, I'm pretty sure if you look on Maxeller, you can find some information. Then if you look for like Xilinx, you'll find some information. It's depending really what you want to do, because they are all customized. Like you want to be able to do lots of operations that involve like multiplication and division, then you have to buy a certain one that is customized for that, depending on what you want to do. And then there are many different price ranges. Okay, thank you.